So for the very last hands-on exercise, there's going to be another exercise tomorrow morning too, but that one is hands-off, so it will more be like a demonstration by Giacomo. But for the last hands-on exercise, we are actually combining what we have learned, and we are developing a shallow water solver. So here is the shallow water equations, like you might have seen them being described in climate, like in NWP and climate. However, this is way too complicated for the purpose at hand, where we just want to see a few nice waves. So we omit most of these terms. And it turns out that what we have on this slide here is enough if you want to animate waves. Like, this will look physically plausible, but it's not going to be physically accurate. So this is more like a computer graphics, computer animation approach than it would be an approach you would like to have in your atmospheric model. But still, we have quite a bit of opportunity here to play with the concepts we have learned. So by now you should be able to see that we have a gradient at the top here and we have a divergence at the bottom here. So if I show this to you, then that's not going to be a huge spoiler. You know how to compute these vector analytical quantities now. And from here, we can already kind of like start to sketch our algorithm. We would initialize our velocity and height fields, right? We have the same time step as before, where we save the initial state and execute the predictor. Then we have the block where we do the spatial derivatives. We need to enforce some boundary conditions because that's a closed physical system here. We need to build up our equations. So what do I mean by that? Well, as you can see here, there are not only the spatial gradients on the right-hand side, but there is, for example, here the gravitational constant and here the height field itself. So we need to respect this to build up these temporal derivatives, and then we consume these temporal derivatives in the corrector and, well, loop around, increase the time as long as the time hasn't reached our final simulation time. And then you can try to implement this and stare at it for a while, and you will notice that this is not working. Basically, nothing is happening. So if we look at the flow of information in this algorithm, we see that we have stuff on edges and we pull it to the cells, but then this is never communicated back to the edges again. So we'll essentially always only execute the first time step if you would do it like this. So we need an additional block, an interpolation block. And this time we just want to be a little bit better than last time. So we're not gonna simply average, but you will have a field prepared for you, which contains linear interpolation weights. So when you do your interpolation from the cells to the edges, you simply need to multiply by a vector containing 1 minus alpha in the first element and alpha in the second element. And then this should work out for the interpolation block. Now it only remains to clarify what happens in the boundary conditions block. And here we're going to be simple again. We want our waves to reflect at the boundary, so the boundary velocity is always going to be 0. And as is customary, we are also going to have a 0 surface gradient at the boundaries. So this time around, you already implemented the time stepper in the diffusion exercise. So for the shallow water exercise, we took that code and we moved it to the driver, so you don't have to deal with this in this exercise. So in this exercise, you would really only implement the interpolation, spatial derivatives, boundary conditions, and then filling in the temporal derivatives. We are again handing you a variable reference, which explains what is in all of these values and which are the ones you need to write to. And afterwards, there are again hints, which first a few how should I say, light pointers. And then at the end, I believe there is a skeleton which already gives away most of the solution. Okay, so this would be the point in time where the people who would not want to have the first exercise being spoiled can either leave or just mute their headsets or their speakers or whatever and stay in, because I would now start with the live coding of the first exercise. So I'm gonna quit my presentation and just give the people who want to leave a minute to do so. I'm also gonna prepare my notebook. Okay, so here we are faced with the still empty notebook, which we would need to fill in. I already gave away the time stepper in the Slack, but basically what we need to do is we need to save our old edge value, because we will need this in the corrector again. So let's just save this and put this into a variable, which could be temporary if the temporary code generation wouldn't be broken. And then we are executing the predictor. So we're going to say predict. So TET, which is the old time derivative of t, which is the predictor step. And now we basically want to execute the diamond. So maybe it helps here to look again at the time stepper.
You have 2 assignments, Matthias.
Matthias, you probably want. Yeah.
What? Sorry?
You put 2 assignments instead of a plus. Sorry, it was a typo.
Thanks. That would have gone sideways. So we would now really like to do is to execute the diamond, right? Such that we could come up with the TE Nebula 2 over here. And if you look at the diamond again, which we can see, let's say here, we see that we need the temperature value not only at the central edge, but only at the vertices outside. And we need these at the same instant in time. So what we are doing now is we are interpolating these edge values onto the node values, such that we have edge and node values at the same instant in time, namely after this predictor was executed. So we have here our interpolation, and this we can do like so. So we're going from vertices to edges to find the values we want to look at, which is our current TE. And now there is different ways to do it. I can just divide this by 6 because I know that this would always have 6 neighbors. I could do it very awkwardly, like by writing the weights vector, where I put 1/6 6 times. But in this case, we need to assume even less, because we were provided a field which stores the number of neighbors. So number, neighborhood, vertices. So even if this mesh wouldn't be structured, we would still get the right thing here. Okay, but now we are finally ready to compute Nebula 2. So which we internally dubbed the diamond. So execute the diamond, right? Or at least part of it. So there is a 2. And here we have a sum over. Okay, and this is, it's going to be a little bit more involved reduction. We have the T nebula 2 here, which we want to fill. And now the question is, well, sorry, what I wanted to say, yes, we have the T nebula 2 here, because obviously we do. But what I wanted to stress is that this is on edges, right? And we want to look at a few vertices. So we know we're going to start at an edge, because this is an edge field, and we know that we want to end up at the vertex field, right? Because TV is on vertices. Now it's not quite clear how the complete chain will look like, but if we go back to our sketch, we can see that at least one way to formulate this is to go from this central edge to the two cell neighbors, and from these two cell neighbors to all the edges. And this is exactly what we're going to do. It's going to be edge, cell, vertex. So what are the operands? Well, the operands at least are simple, right? These are the way, it's TV. And now we're going to see something else, which I believe confused a lot of people, and I'm sorry for that. Is because we still have weights. We have weights to consider. So basically, we're going to, with this reduction, we're going to cover the Tn1, Tn2, Tn4, Tn3, and they are weighted, and they are not weighted the same way. And I wanted to make this simple for people by pre-computing the correct weights, but what I should have done is also reflect this here properly, that this 1/2 should have gone into the squared. Because also if we look at the finite difference stencil, it's L that's squared here. And this would not be the whole length, LVV, but only half the length we need to square. So let's put the appropriate weights. So maybe one thing which was also not made sufficiently clear is that we can rely on the fact that the neighbors are going to be returned in a certain order. Because, well, weights imply a certain order, right? So we need to Tn1 and Tn2 are weighted like this, and Tn4 and Tn3 are weighted like so. And the rule here is that the neighbors which are closer in a graph distance sense are returned first. So you can see that Tn1 and Tn2 is directly connected to the central edge, whereas the other two edges are once removed. So you need to travel one hop further to reach the two of them. Which means that these two are going to be returned first, and these two are going to be returned second. But we may assume no order in which these 1 and 2 is returned, like 2 could be returned before 1, or 4 could be returned before 3. Okay, but this is good enough such that we can put our weights. And to avoid some typos, I'm going to copy this in. I hope that's fair. So let's make this a little nicer. So again, there is no factor of 4 you need to pull out because, yeah, I wanted to make it less confusing and have the weights which you immediately can square in here. Okay. But if we stare at the diamond for just a little bit longer, we will notice that not everything has been taken care of. There is still the central element. And there is no way to also look at the center in current reductions as they are implemented in dusk and dawn. So we will need to subtract from that previous result which we had. And we're doing just that. Here, again, I would like to avoid some typos and hence copy that in. So already too late. This is a TE Nebula tool because it resides on edges. So we simply need to subtract twice TE times inverted primal edge length and times 2 times inverted word length. Okay, and now we are already quite far ahead. There is not that much left to do. One thing we need to do is the boundary conditions, which we can do, for example, like this. If boundary edge, then TE should be 0. So we don't want to evolve the temperature at the boundaries. And then we can basically, we can use an else case, or we can just write it further down. But if we are not at the boundary, we would like to evolve TET by computing the ordinary differential equation, which we had at the very beginning. Like, this is basically forming this part, but in a discretized session. And then there is only one line to go, which we have a predictor corrector time stepper. So we execute the corrector step. Okay, so now let's see what happens. Of course, there is something wrong. So there is no reason to panic, but I realized that this is not at all obvious and our error handling needs some work. Basically, what is absolutely not intuitive is the error which matters is at the end. So dusk complains invalid location type edges. Well, yes, this makes a lot of sense because it's edge singular and it's not edge as. All right, let's give this another go. Okay, now I'm disoriented. Let me try again. Okay, so looks like we're good here. We did not receive any further errors from the pipeline up until the C++ code. So now you're also free to look at what has been generated. So here is the code that drops out of Dawn, so to speak, for the naive backend. Actually, it's more mangled than this, but you are free to execute Clang format on the generated code if you want to look at it. But this is just a side note. So let's go ahead and try to compile also the generated code. So now if mistakes would appear here, that would mean that we messed up over at MeteoSwiss and put a code generation bug, which at least 2 were discovered throughout this workshop. Now we are doing the test. We can see that all our immediately results are correct, which then implies that our stencil is correct. So then we can execute a few hundred time steps. And then finally, we can look at the result, which I have unfortunately already just spoiled, but sure, let's re-encode that video, which takes a few seconds. And what we can see here is our solution simulation on the left. The solution is not like a solution which we pre-computed, but this is the analytical solution. And by the difference between the simulation and the analytical solution, you can see how good our simulation method is. And by this huge peak at the beginning of roughly 0.1, which is about 10% of the input value, we can conclude that our method is very poor. But hey, if you cover the right-hand side of your screen, this at least looks plausible, like a gloss blob that is diffused throughout the domain. Okay, so I hope this was helpful.